Hello everyone and welcome back to I Be Depressed, Smile. My name is Inyadu and I'll be guiding you through today's lesson, which will be on projectile motion. Projectile motion. There you go. And what is projectile motion? Well, projectile motion is a form of motion experienced by an object or particle that is projected near the Earth's surface and moves along a curved path under the action of gravity only. So, for example, if we have little Robert here, and he's smiling because we're doing physics, and he throws the ball, and it fell somewhere like at this kind of path, that is what we call projectile motion. But before we can discuss projectile motion, we're going to have to talk about the addition of vectors and such, for any of it to make sense. A vector is a quantity that has a direction and magnitude. Importantly, vectors are independent of position, as we can move them around as long as they maintain their magnitude and direction. And we usually denote vectors with these arrows. This is a vector, and usually units like 6 meters per second, or something like 4 meters per second square. And if you remember back to our previous video, you know that some quantities are vector quantities, such as displacement and velocity, since they have a set direction. I think we used the example of A and B, where this distance traveled is, it's quite a long distance, but the displacement is just the direct line between A and B. So we say that displacement, velocities, acceleration, all these things have directions and they're vector quantities, while speed, distance only have magnitudes, and thus we call them scalar quantities. It's quite straightforward. Now, what we're interested in is what happens when we add vectors. So, for the sake of the argument, assume you're in some big factory or something, and you have a box. And it's going to get moved around, and we're viewing this box from above. And then you have this little guy, Peter, and he's pushing the box. And we can draw a little vector quantity for that. He's pushing the box 1 meters per second. Now we have another guy named Ronnie, and he's also pushing the box this way in 1 meters per second. Now, which direction does the box go? Well, intuitively, if you think about it, the box doesn't go 1 meter to the right and then 1 meter up. No, it goes like this for as long as you wanted to with a distance, but for now we'll just draw a little shorter line like this. But what is the exact magnitude of this velocity? An exact angle, so that we can determine its direction. So this is where the addition of vectors comes in. So if we leave this box and just make a small point, we know that it moves 1 meter per second and 1 meters per second up. But since we know that vectors can be moved around, we can move this over here. And when you're adding vectors, which is what we're doing right now, you have to start the next vector from the end of the other. And this makes intuitive sense, right? Because you wouldn't start the vector like this, because then you have 2 points of origins, and then that would assume you have 2 boxes. Doesn't really make sense, does it? Anyways, you have 1 meter per second here, 1 meter per second here. And then you know that the box moves something like this. And lo and behold, you know that this is 90 degrees because it's moving up and sideways. So you can find the magnitude of this through Pythagoras, the Pythagorean theorem. A squared plus b squared equals c squared. This is 1 meters per second all squared plus another meter per second all squared equals c squared. C equals root 2 meters per second. And I'm getting out my calculator. If you want to give that an exact values, you could call it something like c equals 1.4 meters per second. And to find the angle, we can use the idea of sines. So this angle can be noted as this theta. We know that sine theta is equal to the opposite over hypotenuse. You should know this from your math lessons. Solving for that gives that theta equals the arcsine of 1 over root 2. Theta is equal to 45 degrees. So, to recap, you can add vectors and you can move them around, but when you add them, you need to be careful that one vector starts where the other ends. So now you may ask, okay, I understand vectors, but you should do more questions just to make sure that you properly integrate this into your mind. But for now, how does this relate to projectile motion? Now, you see, we aren't particularly interested in acting two separate vectors because, you know, Johnny throws the ball and it's moving like this. There's only one actor on them. And this vector might have a velocity of 6 meters per second and might be thrown 30 degrees from the ground by Johnny. But what we're interested in projectile motion is how to go from one vector to two. There's many ways we can do that, right? Because this could be the sum of vertical and horizontal, but you could also make it a sum of like some obscure things, these two vectors, or a sum of like 50 vectors. But that's not really what we're interested in. That's needlessly complicating things. In projectile motion, we're usually only interested in the vertical and horizontal movement of the projectile. And that will make sense when we start doing some questions. Now, if we're going to model the path of this projectile in projectile motion, it would probably go something a bit like this. Because we assume no air resistance, so it's like a perfect curve. And of course, that's not reality. In reality, we have air resistance. And air resistance, for any of you who've thrown a ball, played tennis, football, or anything like that, you know that the ball will slow down and it won't reach probably that high of a height, so it'll probably go like this. That's air resistance, but we're not going to consider that today. But you should know how it works and how to draw it. Now, so you know that you can divide this vector into a vertical and a horizontal one. And if we do this real quick by applying our Pythagorean triangle, you can see that again we can use sines. So sine of 30 times 6 is equal to the opposite, which is equal to, I know the answer, 3 meters per second. So you have 3 meters per second vertical movement, and then the horizontal movement is 6 times cosine of 30. You guys should all know this from your math lessons. And that is equal to 5.2 approximately to 2 significant series. Now, you may ask, what is the maximum height the ball reaches? Or something like that. Well, then you need to be aware of something. Since you're only involved with height, only the vertical movement of the ball matters. You have 3 meters per second here, but you have another different kind of vector quantity acting down, which is acceleration due to gravity, which is 9.81 meters per second squared. Oh, and I should write the questions up there. So, max height question mark. And if you recognize this, acceleration is constant, so we can use Let's do that equations. Now, at the top, what velocity does the ball have? Well, when the ball reaches its maximum height, it starts falling downwards. But at that point, it hasn't started falling downwards yet. So our v value should be 0 meters per second. And our u value is the initial velocity, 3 meters per second. And our acceleration value is 9.1. And we're looking for the acceleration. Sorry, there's just a bit of background noise, but that's fine. And no, we're looking for the distance. So we know the formula v squared equals u squared plus 2as. S equals to v squared minus u squared over 2a. Inserting the values, then, and acceleration is acting negative, of course. Inserting the values then gives 3 squared over 9.81 times 2. So, which yields 0.46 meters approximately. Now you've solved for maximum height. But a more complex question might ask, what is the distance the ball travels before it lands? Well, let's draw this diagram again. And it was always important to remember your units. My handwriting is a bit ugly though, but that's fine. What's the maximum distance the ball lands when it gets here? Well, firstly, you know that you're interested in the horizontal velocity. And that's constant because there's no air resistance for working on it. So it's traveling at 5.2 meters per second. And since velocity is constant, you can just use velocity equals distance over time. And then times velocity equals distance. But then you need to find the time in which the ball is in the air. Alright. So we might consider the vertical movement. And when the ball lands, since it's starting to go up by 3 meters per second, it will also land going in 3 meters per second the other way. This makes intuitive sense. It's going up, it's reaching its point of 0, and it's going down again. So, u equals 3 meters per second, v equals negative 3 meters per second. And then we might apply the formula, and a is again negative 9.8 meters per second squared. And we can apply the formula v equals u plus at, t equals v minus u over a, t equals v, which is negative 3 minus 3, so negative 6 divided by 9.8, negative 9.81, t equals 0.6 seconds. Inserting this back here gives s is equal to 0.6 times 5.2. S is equal to 3.18 meters. This is how far away it lands. Now, that was quite a complex question. So just to summarize, this distance here is 3.18 meters per second. Now, of course, we haven't gone through all the examples, but these are some introductory examples to give you a taste of what projectile motion is about. And hopefully you've learned a lot and you're ready to do your schoolwork. I wish you all the best and you're free to go.